Welcome to Introduction to Quantum Field Theory, Lecture 16. In this lecture, I'm going to continue the discussion of the propagator in scalar quantum field theory. Recall that in the last lecture, we introduced the free propagator as the expectation value of the two-point function phi of x, phi of 0. In this lecture, I want to first concentrate on the zero temperature limit so that we take the result that we found in the last lecture that was given in equation 15.9, and it's reproduced here as equation 16.2 for the present lecture. But a free propagator in the limit of t to 0 is just given as an integral over the Euclidean form momenta k of this particular form. We will interpret and discuss this result in this lecture. If you look at equation 16.2, you find that this is in the form of a Fourier transform. So that we can define a Fourier transform propagator or a momentum space propagator, which we denote by a tilde, that is just given by 1 over k squared plus m squared. Recall that k squared is the form momentum squared, which means that we have the spatial momentum squared plus the Matsubara frequency omega n squared, where omega n are 2 pi t times n, where n is an integer. We can formally write the form momentum squared in a Lorentz invariant form, where we have minus the time-like momentum squared plus the space-like momentum squared if we introduce I omega n as the corresponding form momentum. Now that form here is suggestive, but really what we want to do or have to do is to do a proper analytic continuation of the form momentum from Euclidean space to Minkowski space. Where k mu is the Minkowski form momentum that has k naught, the energy, as a zero order component, where k naught is a continuous variable. From the form that we discussed for the form momentum squared, we find that we can, at least formally, analytically continue the discrete Matsubara frequencies omega n to continuous real momentum k0 by doing the limit I omega n going to k0 plus I times a small positive value. And we have to take this small positive value, this regulator, to 0 at the end. It turns out that if we use this prescription of analytic continuation for the free propagator momentum space, we find that the resulting Green's function that you get is the retarded free propagator in Minkowski space. The corresponding discussion and technology to figure out that this is the proper Green's function that we get is slightly beyond the scope of our introduction to quantum field theory, but if you're interested, have a look at the archive preprint chapter 8 that discusses this in great detail. So if we look at the actual form of the propagator that is analytically continued to real Minkowski momenta k0, we just take the result that we listed in equation 16.2, plug in minus a k naught plus 0 plus for the Matsubara frequency omega n, and we find the result that's given here. Again, since we have to take the regulator to 0 in the end, this result here can be further simplified. So we can expand this result here such that we have the Minkowski momentum, the Minkowski form momentum squared, so that's minus k0 squared plus k vector squared plus m squared, and then there's a part here that comes in as minus I regulator times k naught. That really sort of means that it's a small number times the sign of the Minkowski form momentum, k naught. This result can be further rewritten by taking the imaginary and the real part of the expression and taking the limit of the regulator to 0. The first part here is written as principal value of 1 over k squared plus m squared. And then we have a remaining part here that is of the form of something with a small regulator in the numerator divided by something squared plus regulator squared, which we can recognize to be essentially a representation of the delta function. So we use the limit of the regulator to 0 of this expression going to pi times the delta function to find the second line in the equation that's given up here. So that's the form of our analytically continued retarded Green's function for the free propagator of the scalar field. And it has the form that has some principal value plus an imaginary part that is given by the difference between two delta functions. It turns out that the real and the imaginary part of the retarded Green's functions are not independent. They are related by a certain generalization of the optical theorem. I don't want to really go into much of the details. I will just point out that it's possible to just concentrate on the imaginary part of the Green's function. And if we do that, we can define a new function, which we call the spectral function, rho, that is given as the imaginary part of the retarded correlator. Since only the delta functions in the retarded correlator are imaginary, we find that the spectral function for the free correlator is just given by this expression here, pi over ek, where ek is just square root of m squared plus k squared times the difference of these two delta functions. Because of the delta functions, the spectral function is sharply peaked at the energies k naught being plus or minus ek. We've been deriving this result in quantum field theory, but if you have a spectral function that's sharply peaked, that really sort of is more like a localized excitation that has an energy k naught equal to ek for this first part here. That sort of looks like a particle. If you have an excitation that is well localized in its energy, it's not a diffuse object, it's a very concrete excitation, and we could call this a particle. We can also be slightly more general and say, okay, maybe in the future we'll have things that are not exactly delta functions. They are sort of slightly broader, like Lorentzian shapes, in which case we wouldn't have an actual particle. So to be more general, we'll call this excitation a quasi-particle. That's the part here of the spectral function that's sharply peaked for an energy k naught being ek. However, there's a second contribution here that is formally an excitation that has negative energy. We'll call this an antiparticle, and because it's, again, potentially something that's not quite a particle, they call it an anti-quasi-particle. Antiparticles are common features of quantum field theories, and they emerge naturally if you look at observables such as the spectral function. That gives you some idea of what the spectrum of the theory really looks like. So what we find is that the quasi-particle structure of the spectral function suggests that the relevant excitations in free quantum field theory are particle-like. We can look at the so-called dispersion relation of that spectral function. That is basically just the relation between the energy k naught and the wave number k. And we find that for both the particle and the antiparticle, the dispersion relation is given by equation 16.9. So the energy squared is just k squared plus m squared. And what that means is that since the dispersion relation is often measurable in practice, we have access to the properties of these quasiparticles. In particular, if you can measure the dispersion relation of this particular quantum field theory, for instance, by scattering or other sort of means, then you find that you have a handle on this parameter m that we have in our Lagrangian here. And if you look at the dispersion relation here, that m here really just is nothing else but the mass of the quasi-particle under question. So even though we are doing quantum field theory, at least for the free limit of this quantum field theory, the dominant excitations are particles with mass m. That's good news because that just means that in that limit, the quantum field theory gives back the sort of classical interpretation that we would have given to those excitations in the first place. Also note that the dispersion relation doesn't have any imaginary parts, and you can sort of interpret this as saying that the quasiparticles don't have a width, so their lifetime is basically infinite. They are unconditionally stable in free field theory. As a preview, we will recalculate properties of those quasiparticles away from free field theory, and will generically find that at least some of these quasiparticles will not be unconditionally stable. They will have finite lifetimes, finite width, and we basically should be able to calculate some of these properties there. So they can decay, for instance. And that concludes the present lecture.